We live in a world where gravity and mass often feel like minor inconveniences. Every day, we design structures of towering steel and concrete, and we move massive amounts of earth with the simple push of a button. Building the ancient world was a much more demanding experience. Early engineering lacked exact equations. It relied instead on a grueling process of trial, error, and immense physical struggle. Without automated machinery, moving monumental weight required a purely biological solution. If a stone was too heavy to lift, the answer was to add 50 more sets of human hands to drag it through the dust. That approach began to shift with a Greek thinker living in Syracuse around 250 BCE. Archimedes approached the physical environment from a mathematical angle, realizing that nature was governed by strict, predictable rules. Archimedes turned geometry into a practical instrument. He realized that mathematical precision allowed for the direct manipulation of physical objects and the environments around them. By formalizing equations that accomplished what hundreds of laborers could not, he demonstrated that human intellect could function as a force multiplier, proving that math had the power to move physical mass. Before you can build machines to control nature, you have to find a way to measure forces you cannot even see. While lowering himself into a tub at the public baths, Archimedes noticed the water spilling over the edges. He observed that the volume of the spilled water was identical to the physical volume of the submerged object. This diagram illustrates what he codified next. When an object enters a fluid, gravity pulls it down, but the fluid pushes back. Archimedes determined that this upward push is exactly equal to the weight of the water pushed out of the way. This observation established a method for calculating and predicting invisible interactions in nature. By linking physical mass directly to water displacement, he provided the quantitative basis for fluid dynamics. The next major hurdle was sustaining cities and crops. For centuries, drawing water out of low-lying rivers and moving it uphill meant hauling heavy buckets by hand, hour after hour. Archimedes used geometry to translate continuous spinning motion into a straight, upward climb. Inside a hollow cylinder, he placed a helical blade. As the shaft turns, the spiral scoops water. With each rotation, it's trapped and pushed steadily higher until pouring out the top. The Archimedean screw provided a reliable solution for irrigation. It proved that applying a specific mathematical shape, the helix, could effectively lift water against the downward pull of gravity. Even with clever pumps, human beings still have absolute biological limits. This becomes a terrifying reality when your city is under siege by a massive, heavily armed naval fleet. To defend Syracuse, Archimedes focused on the relationship between input force and distance. He codified the principles of levers and pulleys, formalizing the concept of mechanical advantage. He then applied that mechanical advantage to the battlefield, designing efficient defense mechanisms that could hurl massive stones at enemy ships from safely behind the city walls. Looking at this lever diagram, we see how a small effort applied over a longer distance pivots on a fulcrum to lift an extremely heavy load over a short distance. This meant a single soldier generated the destructive output of 100 men. By translating these principles into iron and wood, Archimedes altered how cities were built and defended. He demonstrated that human capability relies on mechanical ingenuity rather than raw physical size. By measuring water displacement, designing geometric pumps, and calculating mechanical advantage, Archimedes shifted our approach to the physical world from guesswork to exact science. The mathematical frameworks he left behind outlasted the empires of antiquity. Centuries later, those same documents provided the groundwork for scientists during the scientific revolution to decode the universe. His rigorous approach to force and motion provided the foundation that thinkers like Galileo and Sir Isaac Newton used to formulate their own laws of gravity and motion. The practical effects of these ancient calculations are visible at any modern construction site. The mechanical force powering today's heavy machinery relies on the same geometric principles he first identified. Every time we use a lattice of steel cables and cranes to lift massive concrete blocks, we apply his foundational rules of levers and pulleys. When we load massive steel ships, that entire global supply chain stays afloat because of the laws of buoyancy he calculated in a bathtub. Every road we pave, every building we raise, and every load we carry rests on the mathematical legacy of one thinker in Syracuse who used a single mathematical spark to move the world.